Hey guys, welcome back for another chemistry lesson. Today we're going to talk about periodic trends, specifically the trends in atomic radius. So, there are several methods that we use for measuring atomic radius for main group elements, and they give slightly different numbers, but it's the same general vibe. Right? The first way that we can look at it is what we call the van der Waals radius, which is the non-bonding radius. So here I've got two krypton atoms that are not bonded to each other, but they are side by side. We can measure the distance between the two nuclei, divide by 2. That's our radius. And then the other option is a covalent radius, where the two atoms are bonded to each other. Again, measure the distance between the nuclei, divide by 2. Because again, it's the radius, not the diameter, right? So, we've basically distance between two nuclei divided by 2 so that I now have the radius instead. Again, this is going to provide a slightly different number than this, but it's close. So the atomic radius is the average radius between two atoms, right? So, atomic radius decreases across the period from left to right. This probably seems very counterintuitive to you, but this is related to Coulomb's law. And so, as I go from left to right across a period, you'll see here atomic radius decreases from lithium going across to neon. What we're doing is we are adding electrons to the same valence shell, and the effective nuclear charge is increasing. And so what that does is, if you think back to Coulomb's law, we've got an increase in the charge in the middle of the atom. We've got an increase in the charge in the outside of the atom. So the bigger the charge is, the stronger they attract each other. So what it does is every time I add a proton and a neutron, or a proton and an electron, it kind of hugs it a little bit closer and hugs it a little bit closer and hugs it a little bit closer. So the more in a row electrons I add, that means there's a corresponding proton in the nucleus, and I'm going to grab it just a little bit closer and a little bit closer. Alright, as I go from top to bottom in the periodic table, our atomic radius increases going down a group. So again, same graph here, but as I see, I've got lithium, sodium, potassium, rubidium, cesium. This is our alkali metals, and as I go from top to bottom, I'm getting bigger and bigger. And the reason for this is we are adding a principal energy level, which means that our valence shell is further from the nucleus. So the effective nuclear charge is fairly close, right? So we're canceling out all but one of the nuclear charge, but we're further away because I'm adding, think about it like an onion. I'm adding a layer of the onion and a layer of the onion and a layer of the onion every time I go down a row. So here is a periodic table with the actual measurements in atomic radius, and this is in picometers. And you can see general trend. We get bigger as we go down the periodic table. We get smaller as we go across the periodic table. So the size of an atom is related to the distance that the valence electrons are from the nucleus. The larger the orbital that the electron is in, the further the most probable distance is, and the less attraction it's going to have for the nucleus. And then as we go down a group, we are adding that principal energy level, which means the larger the principal energy level, the larger its volume is, the further away from the nucleus it is. So quantum mechanics predicts that our atoms should get larger going down a column. The larger effective nuclear charge an electron experiences, the stronger that attraction is. That's what I explained about, additional protons and additional electrons, right? The more the effective nuclear charge, the stronger the attraction it has for the nucleus. Also, key point on that is the larger that effective nuclear charge, as we go across a row, I'm not gaining any more core electrons. I'm adding all valence electrons. So the shielding doesn't change, which means that we're feeling that difference in charge, right? So the stronger the attraction the valence electrons have for the nucleus, the closer their average distance will be. Therefore, going across the period increases the effective nuclear charge, and we should get smaller as we go across the period. For our transition metals, atoms that are in the same group increase in size as we go down the column, and the atomic radii as we go across the D block is pretty much the same for all of the elements. There's a lot less of a difference, and that's because our valence shell is already full, or mostly full, and that's not changing because we are adding core electrons. So remember, 4s is lower in energy than 3d, but 4s is the valence. So if we fill up 4s and then go and start adding to 4d, or excuse me, to 3d, that's not changing the number of valence electrons. So the effective nuclear charge on those 4s doesn't really change.